Is this a new assignment or same?
No, it's same assignment. Okay, Ohm's Law. We're going to talk about Ohm's. I guess I should put apostrophe S. Ohm's Law, named after a guy named Ohm. All right. And this is the basics of all circuits. And some of you really should think about becoming electrical or electronic engineers. They make big bucks, and we need them. Okay, there's a shortage of them. So, or if you don't want to be an engineer, you can become an electrician or a technician. We need people who understand how to use Ohm's Law out there. So this is important stuff. Now, here's what we've got. We've got some kind of battery. And so it's going to come across here, and it's going to deliver energy to a resistor. So I'm going to call this delta V, and that forces a current to flow. But now what we're going to do is define this quantity R, which we're going to call resistance. And it's a property of this, that resistance is a property of my light bulb. Okay? And here's what resistance says. Resistance, by definition, is delta V over I. Okay? Now, what does that mean? Okay, it says, oh, now, it doesn't really say this, okay? I don't know what you call this in English when you give a personality to an inanimate object. Personification. I'm going to personify the resistor here. The resistor says, you know, in my worst New Jersey accent, it says, oh, you want to go through me? You want to go through me? You want to put current through me? Here's how much voltage you need. You need some energy per unit charge to go through me. You want to put current through me? I don't like current. Okay? I'm going to make you pay. So resistance is how much you got to pay to make 1 amp of current flow. So it's think of the units here. It's volts per amp. It's how much voltage you need to put across a resistor to get 1 amp of current to flow through it. And that's why we call it a resistor, because it resists the flow of charge. Like if something has super high resistance, you need lots and lots of voltage to get an amp of current to flow through it. Yeah. Or something has really, really low resistance, you don't need much voltage at all to get an amp of current to flow through it, as we're going to see here in a minute. We're going to talk about a short circuit here in a second. Now, a volt per amp, we have a name for a volt per amp. A volt per amp is called an ohm, named after a guy. Well, it's named after a guy named Ohm. All right. Now, what would be a logical letter to represent a volt per amp? 1 ohm. Right? Capital O, right? Okay, so what if my resistance here, okay, the resistance is 20 ohms. We got a problem. That's no good. It looks like 200. So we don't do that. An ohm, instead of a capital O, it's called a capital omega. Looks like a little horseshoe. And I'm sure you've seen omegas before. You know, if not, go to a fraternity or sorority house or something like that. It's an capital omega. And it is just kind of a horseshoe shaped, and it looks a lot different than a 0. So that's what we use. So instead of doing that, we would say R equals 20 ohms. Now, what does this 20 ohms mean? It means this. How much voltage will it take to get 1 amp of current to flow through it? 20 volts. I would need to have 20 volts over here to get 1 amp of current to flow through a 20 ohm resistor. That's a lot. 28 volts is a lot. You'd have to get a couple of batteries, hook them up together, so on. Now, this ratio of the voltage, per unit current, this resistance, for some materials it's constant. For some materials it's not. But what we're going to assume is that this ratio of voltage per current is going to be constant. And it's not quite true. In a light bulb, it's actually not true, because a light bulb, the filament gets really hot. And the resistance of the material depends on temperature for this filament. But we're going to pretend that, most materials that we actually use in reality, the voltage doesn't change over a certain range. So, the resistance is a constant. So we're just going to treat resistance like a constant. And really, this is my main equation. This is where we get it from. But we rearrange this equation and say delta V is equal, because we don't like fractions, is equal to I times R. And this right here is called Ohm's law. That's what that equation is called. The voltage drop across a resistor. Now, notice I call it a voltage drop or a voltage loss. Here's voltage gain, voltage loss. That is, I deliver energy to the circuit. Let's say it's 12 volts. 12 joules of energy per coulomb of charge. We deliver, we lose, we put out into the world 12 joules of energy per unit charge. And then we get back to zero. Now my little charge carriers have no energy at all. They come back to the battery. Whoop, they get energy. And then, boom, they lose the energy. Get the energy, lose the energy. And they just keep going, marching in circles around the circuit. That's how electricity works, at least for direct current. Now, the stuff in the classroom is AC current, but we're not going to talk about AC current here. AC current works pretty much the same way. It's a little more complicated mathematically. All right, so we have Ohm's law. And now, let's talk about meters for a second. How do we measure current? How do we measure voltage? Okay, current is measured with an ammeter. I don't know why they leave the P off. It should be called an amp meter, but it's not. Why? Because electricity and magnetism has to be as confusing as possible to students. It's almost like they've designed this thing to be confusing. So don't worry. I don't know. If you call it an amp meter, I will not mark it wrong, okay? Because I think it should be called an amp meter, but they leave the P off, an ammeter. And here's the symbol we use for it. We use an A with a circle. Now, this is a device that we use to measure the current. And so here's a wire, and it just goes into the ammeter and comes out of the ammeter like that. So in my circuit over here, if I wanted to measure the current flowing through here, I would just put the ammeter like that. Put it in the middle of everything. So there's my ammeter. Voltage is measured with what do you think we're going to call it? A voltmeter. Now, I think to stay consistent with ammeter, it should be called a voltmeter. But they don't. They leave the TN. I don't know. Don't blame me, okay? I'm just the messenger. Okay, a voltmeter. Now, what does a voltmeter measure? It measures how much the voltage changed from one side to the other side. And so, let's say we have a resistor. We always take a lead. You know, you've seen meters, and you see people with wires and leads. They call them leads. we put the voltmeter across the circuit element. It's called being in parallel with it, but you just put it across. So this is going to say, okay, how much energy per unit charge is being changed when I go from the top to the bottom, or from the bottom to the top, depending on how you're doing it. And it really gives you a voltage difference between here and here. How much more energy is up here than down here, all right? And you can measure it across the battery as well. So you take your voltmeter and hook it up like this. And this might be how much does the voltage increase from here to here. And over here it might be how much does the voltage decrease from here down to here. It all depends on how you hook it up. So if I go back to my circuit over here, I would hook a voltmeter up like this. Like that, across the circuit element, or a voltmeter across the battery. But the ammeter you just stick the wire in and take the wire out. And this is called, the ammeter is in series with the circuit. The voltmeter is parallel to, see how it's parallel like this, two lines that are parallel to whatever circuit element I'm trying to measure the voltage difference across. Okay, almost done. Let's talk about power again. We said that the power delivered to the circuit, or the rate at which energy leaves the circuit, depending on whether you're talking about a resistor or a battery. Let's take a look at the battery. I times V, right? Current times voltage gives me the power. Now, one thing I didn't mention. Power is energy per unit time, right? Energy per unit time. So I'll just call this E over T. So you're going to have a homework problem where they want, okay, how much energy do you use in 5 minutes? Well, if you know the power, current times voltage, and you want to know how much energy, just multiply that by time. So energy, E for energy here, is equal to IV times T. Current times voltage times time. Now you got to know what all these variables mean, and we're going to create a quantity chart here in a minute. Now, so here's my equation for power. Here's my equation for voltage. I can do a substitution. What if I said, well, V equals IR and P equals I times V. So if P equals I times V, but V equals I times R, we get a very famous equation. You quite often see the power given off by a resistor is equal to I squared R. I times I is I squared times R. So there's another way of expressing the power that comes out of a resistor. Usually you use this for resistors. Usually you use this for batteries. They both involve current. This is the power into the circuit. This is the power out of the circuit. They should be equal to each other if you only got one resistor. And of course, if you want to know how much energy, just multiply this by time and you'll get it. You'll get the energy. Okay, now we've covered a lot today. So what I'm going to do is I'm going to create what I'm going to call a quantity chart. And in your outlines that I'm going to have you do, there's 5 different outlines. I'm going to have you write a quantity chart. You're leaving early. Okay, so whatever. So what are the quantities that we've dealt with so far today? Let's look right here. We dealt with charge. That's kind of a basic one. So we've got charge. Let me zoom in. charge. We've got current. We've got voltage. We've got power. And then over here we've got resistance. Okay. And is that it? Okay. Yeah, these are the 5 quantities that are new. I mean, we have time. And power we've covered before, but we didn't spend that much time on it, so we might as well review it. Now, what I'm going to do is create a chart for you that's going to help you review this stuff, because we're going through it pretty fast. So this is the quantity. So this is the quantity. The next thing I'm going to put is the variable. Right? The shortcut name we give it. What was the variable for charge? What letter did we use to represent charge? Q. What was the letter we used, the variable name for current? It was I. Voltage. Power. Resistance. R. So current and charge are kind of weird, but voltage, power, and resistance are easy. Just the first letter. Now we're going to talk about the units. And by the way, this is a quantity chart where you have the quantity, the variable, and the units. What units do we have for coulombs? I mean, for charge. Coulombs. I hate it when I do that. And we use the letter C to abbreviate it. So you put the unit and its abbreviation. Now for current, we have amps and the letter A. But what is an amp? It's a coulomb per second. So you kind of break it down a little bit. Like, what is it in terms of its, what makes sense? Now, voltage is measured with what unit? Volts, which we abbreviate with the letter V. But wait a minute, what did I do right here? Let's go back up to the amp. So like 1 amp is equal to a coulomb per second. What is 1 volt? Is equal to 1 joule per coulomb of charge. And you got to remember that. Voltage is how much energy I give per unit charge. It's per unit charge. Okay? Now power is measured in watts. And we use the letter W for watts. And 1 watt is a joule per what? Joule per second. It's the rate at which energy is being delivered. So volts is a joule per coulomb, and a watt is a joule per second. Yeah. Now resistance. What was resistance measured in? Ohms. We used a capital omega to represent ohms. And we have 1 ohm is, remember that resistor that from New Jersey, oh, you want to go through me? This is how many volts you need to put 1 amp through me. You want current to flow through me? You're going to pay a price. So this is the price you pay. It's the 1 ohm is 1 volt per amp. Now, by the way, you can break volts down to joules per coulomb. You can break amps down to coulombs per second, and then a joule is a kilogram meter squared per second. You can get all those fundamental units, and you can drive yourself nuts. This is really all you need right here. This is what you need to understand about these units. Okay, finally, let's just write a little equation list. We've got the quantity chart. So let's write below it. Okay, write an equation list for all these. Oops, let me zoom out a little bit. Not that much. Oh well. So what do we know? Well, current is equal to how much charge flows by divided by the time it took. So there's one equation you need. You need power equals I, the current, times the voltage, which can also be I squared R. So here's the power delivered by the voltage of a battery. Here's the power that leaves a resistor. Okay, they should be equal to each other in a circuit because you have to conserve energy. Then we have Ohm's law, where a change in voltage across a resistor is equal to the current times the resistance. Now, this really comes from the definition of resistance. We just rearranged it a little bit. Oh, and then finally, related to this one, related to this equation, remember that energy is equal to power times time. Remember that. Power times time is equal to energy. Now, sometimes you know, power in kilowatts times time in hours. We talked about kilowatt hours, but we did that a little bit earlier before. But, or you can, if this is in joules per second and this is in seconds, you'll end up with just plain old joules, which is just fine. But these are the equations that you will use to do the homework today. Okay. Any last questions?